Welcome to the course on Introduction to Electrical Engineering. We will discuss today lecture 9 and the topic is transient response of second order circuits. Well, in this we would like to talk about as I outline some of the insight and real life application where this second order systems are used. Then we would like to introduce of course, with basic concept and source free series and parallel RLC circuit responses or analysis, and then we will talk about the different conditions into that which really responsible for different kind of responses like underdamped, overdamped and critically damped responses, and then we will like to of course have some exercise in numerical analysis and followed by references. So, now coming to why we have to study this RLC circuit as we call it second order system, because there are two energy storage element into RLC circuit like L and C. So, there are some practical examples where we really use such circuit like, and these are some of the really real time or real life application. Example is which is very upcoming applications like of RCRL and RLC circuit like wireless power transfer. I mean this wireless power transfer, Tesla has given a concept in 1988 which was repeated in typically after around 125 years later in MIT as an experiment in typically in 2007, and the industry started developing the product like as wireless charger for electric vehicle in 2011. So, this is the same concept like it is here that we apply the voltage source, then we have a like kind of transmitter which have antenna or coupling devices followed by receiver and then load. And now, this wireless transfer is this is just generalized block diagram, but it is very extensively used. You might have seen lot of application even the charging of now mobile phone which will have some of the typical photograph little later. So, this is the basic concept of this of wireless transfer. We have a single phase AC mains followed by high voltage transformer with the typically a capacitor and then a spark gap with followed by another transformer which produces the typically the high voltage. So, say we call it like a Tesla coil circuit, a non lamp glows near the Tesla coil due to the movement of electrons through nearby air, that is as you can see in the typically in the photograph like. So, there this concept now practically use this wireless power transfer in many applications like radio frequency identification, RFID technology, and then the passive tag consists of coil antenna that transmit the data back to the RFID reader in closed vicinity and as RFID shopping tags, as you can just clearly see the, and then you can have typically now this concept probably you will understand more to day life. We have application of such in wireless transfer for RFID based toll collection card on a smart card. You bring closer to your smart card closer to the your typically ATM machine, and then you are able to is able to recognize clearly this concept of fast tag or otherwise the technology have been extensively used in many applications of real life practical applications like. So, the basic concept is of this typically the inductive wireless charging. I mean as you can see that I mean even in case of wireless you can call it mobile phone. I mean we have here the power source as the basic source, we have an oscillator which produces high frequency, and then we have another side another coil which receive followed by rectifier and feed the load, the power goes. So, then you have a certainly I mean two sides of the coil which are really kind of wireless, and typical example here I mean you have different parts of this of kind of mobile charger here like. So, you have a plenty of like not only left on the mobile phone charging, but it is also now use electric bus by cast in Korea for dynamic inductive wireless charging as well as static charging. I mean it is used as a static charger for electric vehicle as well as it is used dynamic wireless charging, and that really gives the advantage that you can reduce the size of the battery, because your I mean like you already have a network with the from which you can typically charge your battery of the in the vehicle like. Example typically the another concept that was typically magnetic and now it is a capacitive coupling wire power transfer is also there. So, in that case what you have typically a power source followed by couple of capacitor through which energy transferred by it followed by the rectifier, because this is high frequency and You can see on this 2 capacitor can be as a symbolic 1 capacitor. So, you are just having a passive plates and then you have oscillator followed by your capacitors and then you have a rectifier feeding the load like also. That is the basic concept of capacitive coupling wireless power transfer. And well, there are many such circuit, of course, like in antenna array as well as simplified antenna circuit. As you can see the circuit here, you have inductor capacitors as well as resistance as a part of the circuit in this typically kind of applications like. And then of course, current transducers, I mean you are again have a typically eyes providing the Hall effect current sensors, I mean of different makes, or as well as the typically the current probe, I mean used for typically in many power electronics application as well as for purpose of instrumentation and recording like and typically your application in the as a current transformer, I mean which is also responsible for measuring the very high current with the help of this current sensor. And on second you have a very let us say low amount of current, so that you can use the meter of low rating like So, all these use the concept of R, RC, RL or RLC circuit concept in all these applications, or you have a inverse current limiter as you can see the circuit here, as well as you can see the typically inductor with the kind of with the Faraday core, or you have a like electric circuit breaker, or you have electronics oscillator, or you have a like a lightning arresters, you have a spark gap transmitter where you can just see here RLC circuit of different kind, or you have a typically like a single phase induction motor with which you have a inductor resistance capacitance in the circuit RLC circuit, or you have a typically for instance electronic ballast where you I mean normal ballast, magnetic ballast as well as later on electronic ballast, or you have a tune circuit oscillator and RC oscillator. So, where you are using these all RLC component into it, or you have a RLC projector lamp or electric light dimmer, or you have LCR meters, or you have model RLC compression load cell, or you have CFL bulb in the sun, CFL electronic ballast, or you have a line trap circuit which tuned for a particular frequency. You can see the signal of that on the line, I mean like a parallel trap. So, these are the some practical application of these RC and RLC circuit. Now, coming to the basic introduction on this, today we will like to deal with the RLC circuit containing both an inductor and capacitor, and that is 2 energy storage elements, and these circuit have a wide range of application including oscillators, frequency filters, flight simulation and modeling of course, automobiles and function. And the response of this RLC circuit with DC source and switches consist of natural response and force response. This we call it V t equal to V f as a function of t plus V n as a function of t. So, the complete response must satisfy both initial condition and final condition of the force response, and second order circuit responses are described by second derivative differential equation. So, coming to the basic concept of it, like finding an initial and final values of it. So, the objective is to find V 0 I 0, dV 0 dt and dy by 0 dt and I infinity and V infinity virtually for these variables at the infinite time. So, there are two key points here, the direction of the current and the polarity of the voltage, and V and I define according to the passive sign convention. As you can see here, current is entering to a passive device. So, we give a convention to the voltage with the plus and minus in this polarity like. And then of course, you can have a typically the different type of capacitors. You have a fixed capacitor or variable capacitor. When current is entering, you can just see the polarity how it is really explained. And similarly, in the inductors also, whether it is a air core inductor or is a your air core inductor, or you have a air core inductor with the variable air gap. So, that inductance is varied. So, these are the typical symbol, and how the voltage convention when current builds up or current flows through that, how the convention is there. Of course, when current increases, it will be in this manner, when current decreases, it will certainly oppose, but we are considering the convention of in this manner. So, we can say in this typically capacitor circuit, we can say capacitor voltage is always continuous. So, we can say V at 0 t plus or 0 plus will be equal to capacitor 0 minus, because capacitor voltage cannot change very quickly. Similarly, inductor current also is continuous, it can also not change quickly. So, I 0 plus will be equal to I 0 minus like. So, now the learning objective of today we like to discuss to be able to determine the natural response of parallel and series RLC circuit, and to understand what are the initial condition in RLC circuit and how to use them to determine the expansion coefficient of the complete solution. So, what do the response curve of overdamped, underdamped and critical damped circuit look like, and how to choose RLC values to achieve fast switching or to prevent overshooting, avoiding the damage like. So, now coming to the first, the source free series and parallel RLC circuit analysis. So, considering the given circuit here RLC circuit, the circuit is being excited by energy initially stored in the your capacitor and inductor. That is why we call it a source free series RLC circuit, means how the energy there in the circuit, in the sense volt, capacitor may be charged or and circuit if has a inductance. So, inductance also store the energy. So, it means this circuit can have the energy in the energy storage element like L and C, like when current, it depends on of course circuit operating conditions how it is going to be. So, we like to discuss response of this series RLC circuit. So, the energy is represented by the initial capacitor voltage V 0 and initial inductor current I 0. Thus, at t equal to 0, V 0 will be 1 upon C minus infinity to 0 I dt, and that we can call it V 0, and I 0, that is the current in the inductor at time t equal to 0 will be equal to I 0. So, these we call it the like a initial conditions for energy storage element like. Now, for this RLC circuit, now we can apply the Kirchhoff's voltage law in this loop. So, we can just clearly see here I R I plus L d by dt plus 1 upon C minus infinity to t I t dt equal to 0, and on differentiation of this whole equation and dividing it by typically differentiating. So, it will cause dividing by inductance. So, it will become d I d square I upon dt square plus R upon L d I upon dt plus I upon L C equal to 0, where we are considering this I as a variable in this circuit as in the loop as a loop current like. So, that is the, you can call it second order differential equation, and that is the reason we call it this circuit itself as a second order. So, this equation further can be written like d I square upon dt square plus R upon L d I by dt plus I upon L C equal to 0. So, this is a second order differential equation, and it is the reason for calling the RLC circuits second order circuit. The initial value and first derivative are given here. So, we can call it like a typically R I 0 plus L d I 0 upon dt plus V 0 equal to 0 and d I 0 upon dt equal to minus 1 upon L in bracket R I 0 plus V 0 bracket closed like. So, these are typically corresponding to the initial value and first derivative of the initial values like. So, now we can consider for the solution of this, if we consider let the I equal to current, that is a e to power s t, where a and s are the constant, and substituting this value for this I, we can obtain a s square e to power s t plus a r upon L s e to power minus s t and plus a e s t upon L c equal to 0. Then we can take a e to power s t out. So, equation becomes s square plus r upon L s plus 1 upon L c equal to 0. Now, equation with the parenthesis equating the parenthesis part of it to 0, because out of this two term, either this term or this term, one should be 0. Of course, we know this will not be 0 because current is flowing, then that is the value of the current virtually. So, if current is not 0, it means this part is 0. Then if this part is 0, then we can say parenthesis part is 0. So, this quadratic equation is known as the characteristic equation of the differential equation. So, that comes as a form of s square plus r upon L into s plus 1 upon L c equal to 0. And the roots of this equation dictate the characteristic of current, and they are given as S 1 equal to, and this is the quadratic equation. So, solution of quadratic equation you can write here as a 2 root S 1 equal to minus r upon 2 L, that is you can call it B plus under root your a square minus L c. So, you can say minus r upon 2 L plus under root r upon 2 L square minus typically 1 upon L c, and S 2 will be your minus r upon 2 L minus under root r is r upon 2 L square minus 1 upon L c. So, these are the two roots which can be written in more compact form of expressing the roots. So, you can write S 1 equal to minus alpha plus under root alpha square minus omega square, and S 2 equal to minus alpha minus under root alpha square omega square, where alpha we can define r upon 2 L and omega 0 we write upon under root L c. And the root S 1 S 2 are called the natural frequency, and because they are associated with the natural response of the circuit, and omega 0 is the resonant frequency or strictly at the underdamped natural frequency and expressed in radian per second. Well, alpha is the Napier frequency expressed in Napier per second, and Napier being the unit of the attenuation, and the expression given is modified in terms of alpha and omega 0. So, now this we can write that equation, original equation S square plus r upon L S plus 1 upon L c equal to 0. We can write now S square, of course, r upon L we can equate to 2 alpha S from the previous equation plus omega 0 square equal to 0. So, that is again the quadratic equation in much simplified fashion, where we have defined the two new terminology like alpha and omega 0, and the two values of S indicate that there are two possible solutions for I, and these two solutions we can say I 1 equal to A 1 e to power S 1 t and I 2 equal to A 2 e to power S 2 t. A complete or total solution of this equation would therefore require a linear combination of I 1 and I 2. So, thus the natural response of the circuit series RLC circuit will be I t equal to A 1 e to power S 1 t plus A 2 S 2 power S 2 e to power S 2 t. Now, we can write this equation again I t equal to A 1 e to power S 1 t plus A 2 e to power S 2 t, and we can of course define the different terminology here, where the constant A 1 A 2 are determined from the initial values of I 0 and d I 0 upon d t, and these three types of solution are inferred of this equation. The one is that if alpha greater than omega 0, we call it like overdamped case, and if alpha equal to omega 0, then we call it like a critical damped case, and if alpha is less than omega 0, we call it as a underdamped case like of the responses, what response this typically the equation give with this circuit. So, coming to first case as a overdamped case, where alpha greater than omega 0. So, we can say alpha greater than omega 0 implies that C is greater than 4 L upon R square as a component value, like because we have RLC circuit, these are the component RLC. So, when this happens, both roots S 1 and S 2 are negative and real, and response is given here I t equal to A 1 e to power S 1 t plus A 2 power S 2 t, and that is overdamped response. You can just see this red color, that is the current variation with respect to the time of this circuit like RLC circuit, if it is this condition of the elements is satisfied, which we call it overdamped case alpha greater than omega 0. Now, second case we call it critical damp when alpha equal to omega 0, and or you can call it alpha equal to omega 0 is nothing but C equal to 4 L upon R square. That is the relation between the component of RLC circuit, and we can call it S 1 equal to S 2 equal to minus alpha equal to minus R upon 2 L, and for this case we say I t will be A 1 E s minus alpha t plus A 2 e to power minus alpha t, and this will be A 3 e to power minus alpha t, because e to power minus alpha t can be taken out, and where A 3 will be equal to A 1 plus A 2, and this cannot be a solution because the two initial conditions cannot be satisfied with the single constant A 3, and this is what we call it critical damped response, and we can say peak will be appearing at the time where the t equal to 1 upon alpha. Like now, coming to the typically the solution, typically of solving the response for that. So, alpha equal to omega 0 equal to R upon 12, then we said d I square upon d t square will be plus 2 alpha d I upon d t plus alpha square I equal to 0. Then we can take a you can call it divide into algebraically into two parts like d upon dt. In parenthesis we can say d I upon dt plus alpha I, and plus alpha again in bracket we call it d I upon dt plus alpha I equal to 0. So, we can say we can define this bracketed quantity as f that is equal to d I upon dt plus alpha I. Then we can say this equation modified to first order differential equation d f upon dt plus alpha f equal to 0, and the solution of which is a now first order differential equation with the solution f equal to a 1 e to power minus alpha t, where a 1 is the constant, and the equation becomes d I upon dt plus alpha I equal to a 1 e to power minus alpha t, and then we can typically have the, you can say we can multiply e to power alpha t on both the sides. So, e to power alpha t dy upon dt plus e to power alpha t alpha equal to a 1, and then where the d upon dt e to power alpha t I equal to a 1. On integration of this, so it will be a e to power alpha t I equal to a 1 t plus a 2 and I will be equal to in bracket a 1 t plus a 2 into e to power minus alpha t. So, that comes the solution of it. Here the natural response of critical damped circuit is a sum of the two terms and a negative exponential and negative exponential multiplied by a linear term. Now, coming to third case, which we call it underdamped case, alpha less than omega 0. So, for alpha equal to less than omega 0 means C is lesser than 4 L upon R square. The roots may be written as now S 1 equal to minus alpha plus under root minus omega 0 square minus alpha square, and that becomes equal to minus alpha plus j omega d, and S 2 is equal to minus alpha minus under root minus omega square minus alpha square, and that becomes minus alpha plus minus j omega d. So, where j is under root minus under root 1 and omega d is under root omega square minus alpha square, it is called the damped frequency, and both omega 0 and omega d are natural frequency because they are help to determine the natural response of the this system. Like, so, now omega 0 is often called the underdamped natural frequency and omega d called the damped natural frequency, and the natural response of this now will be I t equal to a 1 e to power minus alpha minus j omega d t plus a 2 e to power minus alpha plus j omega t into t, and we can take out the e to power minus alpha t, and in bracket it goes a 1 e to power minus j omega d t plus a 2 e to power minus j omega d t. And by using Euler's identity, we can just express, of course, some of the term like I t equal to e to power minus alpha t. We can expand the first exponential part a 1 cos omega t omega d t plus j sin omega d t t plus a 2 cos omega d t minus j sin omega d t, and it further expressing it equal to minus e minus alpha t and bracket a 1 plus a 2 into cos omega t t plus j a 1 minus a 2 sin omega d t, and that finally becomes equal to e to power I t equal to e minus alpha t and bracket b 1 cos omega t plus b 2 sin omega t. And you can call it with the presence of sine and cosine function, it is clear that the natural response of this case is exponentially damped and oscillatory in nature. So, response has a time constant of 1 upon alpha and period is t equal to 2 pi omega d. As you can see, the response of this is like a oscillatory response with the providing the damping and the where the period is shown as well as the damping coefficient is also shown, like how it is decaying. So, decaying term is also there with the dotted shown e to power minus t, and it is the periodic function, it is also we can see it shown here like. So, conclusion from this, the damping effect is due to the presence of resistance, and damping factor determines damping factor alpha determines the rate of at the rate at which the response is damped. If r equal to 0, then alpha equal to 0, and we have an LC circuit with 1 upon LC as a undamped natural frequency, and since alpha less than omega 0, in this case the response is not only underdamped, but also oscillatory. And the circuit is said to be lossless because the dissipating or damping element is absent, that is 0 R, and by adjusting the value of R, the response may be made underdamped, overdamped or critical damped or underdamped like. So, it can be satisfying probably the for underdamped also. So, the oscillatory response is possible due to the presence L and C, and the damped oscillation exhibited by the underdamped response is known as ringing. It stems from the ability of the storage element like L and C to transfer the energy back and forth between them due to oscillations. So, overdamped has the longest settling time, because it takes the longest time to dissipate the initially stored energy, and if we desire the fastest response without oscillations or ringing, the critical damped circuit is the right choice. So, now coming to that is the case of series RLC circuit. Now, we will consider the case of the series parallel RLC circuit. As you can see, R, L and C are in parallel, and of course, here also you can consider that inductance and capacitor can store the energy, like because they are energy storage element. So, we can consider the parallel RLC circuit assuming initial inductor current I 0 and initial capacitor voltage V 0, where I 0 small I 0 will be equal to I 0, that is 1 upon L and minus infinity to 0 V t dt, and this V 0 is equal to V 0, this V at the time 0 equal to V 0. These elements are in parallel and they have the same voltage across them. Applying the KCL at the top node, give 1 upon V upon R, that is V here, V upon R, that is the current flowing into resistance, then 1 upon L minus infinity to 0 V t into dt, that is the typically you can call it like a corresponding to the inductor, and then the capacitor, that is the current C dV upon dt equal to 0. So, that is you can call it the equation for this nodal equation, only single node is there, so that is the single equation is there. So, taking the derivative with respect to t of this circuit, t square V upon dt square plus 1 upon R C dV upon dt plus 1 upon L C into V equal to 0. The only difference compared to the series circuit is here, there we have taken V I as a variable, here we are taking as a voltage as a variable, that is the voltage across all the element, their current was the same in all the element like. So, characteristic equation now is given S square plus 1 upon R C S plus 1 upon L C equal to 0, and roots of the characteristic equation, two roots of characteristic equation are S 1 S 2 equal to 1 upon 2 R C plus minus under root 1 upon 2 R C square minus 1 upon L C, and S 1 S 2 again can be represented as minus alpha plus minus under root alpha square minus omega square, where alpha we define 1 upon 2 R C and omega 0 again 1 upon under root L C. Now, we can come all the three cases what we discussed already in case of series circuit, in this parallel circuit also. So, overdamped case is alpha greater than 0. So, alpha greater than 0 means when L is greater than 4 R square C. So, roots of the characteristic equation are real and negative, and response is V t equal to A 1 e to power S 1 t plus A 2 power A 2 e to power S 2 t. And second case of critical damp case, where alpha equal to omega 0, and for alpha equal to omega 0, L equal to 4 R square C. So, roots are real and equal, so that the response is V t equal to A 1 plus A 2 t into e to power minus alpha t. And the third case of underdamped case, where alpha is less than omega 0. So, when alpha equal to less than omega 0, L is less than 4 R square C, and in this case the roots are complex, but and may be expressed as S 1 2 equal to minus alpha plus minus j omega t, where omega d is defined under root omega square minus alpha square, and V t will be e to power minus alpha t in bracket A 1 cos omega d t plus A 2 sin omega d t, as we got the similar kind of solution as we got in RLC circuit, only the difference here is the voltage, there it was the current in response like. So, the constant A 1 A 2 in each case can be determined from the initial condition. So, we have to find out V 0 and dV 0 dt. So, it can be obtained from the same equation V upon R, V 0 upon R plus I 0 plus C dV 0 upon dt equal to 0, and from this we can find out the again first order equation dV 0 upon dt equal to minus V 0 plus R I 0 upon R C. And if you look into three response similar to that with the analogy, here you can see overdamped response with the time, or critical damp, or underdamped response like, of course, in terms of V. So, now coming to the solved numerical problems, coming to the problem number 1, the switch has been closed for long time and it is open at t equal to 0, find the I 0 plus V 0 plus, and second case d I 0 plus upon dt and dV upon dV at 0 plus upon dt, and in C case I infinity and V infinity, typically you can call it the I and V in infinite time, and the circuit is shown here. So, you can just see switch was initially closed for long time and now it is open at t equal to 0. So, now the solution will be, if the switch is closed for long time before t 0, it means that the circuit has reached steady state at t equal to 0, and DC at DC steady state the inductor acts as like a short circuit, and while the capacitor acts as a open circuit. So, solution at t equal to t 0 minus is your the circuit typically as you saw here t at t minus. So, it will be I 0 equal to 12 upon 4 plus 2, and this will be 2 ampere, current is 2 ampere, and V 0 minus will be 2 I 0. I mean that the typically you can call it voltage across these 2 ohm resistance, that will be 4 volt, and that is exactly the voltage will be across this capacitor here like. So, at the and current will be in the inductor. So, as the inductor current and the capacitor voltage cannot change abruptly. So, I 0 plus will be equal to I 0 minus and equal to 2 ampere, and V 0 plus equal to V 0 minus will be equal to 4 volt. So, these are the two initial conditions of this circuit, we got it in the circuit, and now at t equal to 0 plus the switch is open and same current flows through the both the inductors and capacitor, and hence we can say I c 0 plus equal to I 0, and that is 2 ampere. So, now we can say in this circuit initially we start from current 2 ampere, and I c equal to C upon dV upon dt, or dV by dt you can call it, it will be I c upon C, and we can say C dV 0 upon dt equal to I c 0 upon C equal to 2 upon 0.1, this will be 20 volt per second, and V L we can find out L di by dt equal to di L upon dt equal to V L upon L. So, V L is the obtained by applying the Kirchhoff's voltage law in the loop, and that will be equal to minus 12 plus 4 I 0 plus V L 0 plus V 0 equal to 0. So, V L 0 now we can find out from there, that is typically if we take all quantity on other side 12 minus 8, because current have been 2 ampere. So, 4 into I will be 8, and V L is typically 4. So, that is minus 4, typically V 0 is 4 volt. So, that is equal to 0. So, you can call it the V L 0 will be 0, that is the inductor voltage will be 0, and di 0 plus upon dt equal to V L upon dt, that will be 0 upon 0.25, that is 0 upon 0 ampere per second like. So, now coming to for t equal to greater than 0, circuit undergoes the transient, and at t infinity the circuit reaches a steady state again, the inductor acts like a short circuit and the capacitor behave like a open circuit, and we get the I infinity equal to 0, and V will be charged to the 12 volt, typically the capacitor will be charged to 12 volt like. Well, coming to the problem 2, for the given circuit R equal RLC circuit, series RLC circuit, R is given 40 ohm, L is given 4 Henry, and C is given 1.4 farad. Calculate the characteristic roots of the circuit. Is the natural response overdamp, underdamp, or critically damped? So, we can find out here alpha equal to R upon 2L, that is 5, and omega 0 1 upon under root LC, that is equal to 1, and from this we can find out the roots. S1 equal to minus alpha under root alpha square minus omega square, and S2 equal to minus alpha minus under root alpha square minus omega square. So, putting the value we will get S1 equal to minus 5 plus under root 5 square minus 1, and S2 equal to minus 5 minus under root 5 square minus 1. So, these two roots comes like S1 equal to minus 0.101 and S1 equal to minus 0.9899. So, alpha is typically greater than omega 0. So, we can conclude that the response is overdamped, and this is also called evident from the fact that the roots, both roots are real and negative. So, now coming to the problem 3, find the IT in the circuit, assuming that the circuit has reached steady state at t equal to minus 0. So, for the t less than 0, the switch is closed and the equivalent circuit shown is here. I mean, when circuit is closed, your circuit will be of this nature. I mean, the capacitor will behave like open circuit and the inductor behave as a short circuit. So, the circuit will be in this manner, and you can typically find out here, I mean like after this, when this switch is open, I mean then this capacitor this I mean will go, this voltage across this will go to across the capacitor, and you will have a inductor capacitor in parallel like. The switch is closed means this will be the circuit which is shown here, but here of course you will have a charge capacitor with the typically the both resistance in series with the inductance. So, this is the circuit when switch is typically open circuit. So, at t thus at t equal to 0, the I will be equal to 10 upon 4 plus 6 1 ampere, and V 0 will be 6 I 0 equal to 6 volt, and for t greater than 0, the switch is open and the voltage source is disconnected, and the equivalent circuit in now figure B and the roots of are calculated as follows. The alpha equal to r upon 2 l, that is 9, omega 0 is 1 upon under root L C, that is equal to 10 from the element value, and then S 1 is equal to minus 9 plus under root 9 square minus 100, and S 2 will be minus 9 minus 9 under root 9 square minus 100. So, roots are S 1 S 2 will be 9 minus 9 plus minus j 4.359, that is typically for t greater than 0. These are the typical roots, two roots of this, that is an oscillator nature with hence the response of underdamped circuit alpha less than omega, that is I to power I t equal to e to power minus 90 in bracket a 1 cos 4.3959 t plus a 2 sin 4.39 t, and a 1 and 2 are found using the initial condition. So, at t equal to 0, I 0 equal to 1 ampere equal to a 1 and di by dt at t equal to 0 minus 1 upon L and r I minus V 0, that is minus 6 ampere per second, taking the derivative of I t, that is d upon dt, that is minus 9 e to power minus 90 a 1 cos 4.359 t plus a 2 sin 4.359 t plus e to power minus 90 by again 4.359 and in bracket minus a 1 sin 4.359 t plus a 2 cos 4.359 t, and that you simplify to minus 6 equal to minus 9 in bracket a 1 plus 0 or 4 plus 4.359 in bracket minus 0 plus a 2 and substituting a 1 equal to 1. So, you get equation for a 2 minus 6 equal to minus 9 plus 4.359 equal to a 2, and a 2 comes equal to minus 0.6882, substituting a 1 a 2 yields the complete solution as I equal to e to power minus 90 and in bracket cos 4.359 t, that is a 1 is 1 and plus a 2 is 0.6822 in bracket sin 4.359 t in ampere. So, that is the final solution of this circuit like under you can call it natural response like. Now, coming to the problem 4, in the given parallel circuit, find parallel circuit of RLC, find the V t for t greater than 0, assuming V 0 equal to 5 volt, I 0 equal to 0 ampere, L equal to 1 Henry and capacitor is equal to 10 millifarad. Consider the three cases, R equal to 1.923 ohm and R equal to 5 ohm and R equal to 6.25 ohm. So, coming to case 1, if R equal to 1.923, we can find out alpha equal to 1 upon 2 R C for parallel circuit, that is equal to 1 upon 2 into 1.932 into 10 power 10 into 10 power minus 3 equal to 26, and omega 0 is 1 upon L C, and that is 1 upon under root 1 into 10 power minus 3, that becomes the 10. So, these are the typically you can say alpha and omega 0 in this case. So, since alpha greater than 0, the response is overdamped and the roots of the characteristic equation can be calculated from S 1 equal to minus alpha plus under root alpha square minus omega square, and that is equal to minus 2, and S 2 will be minus alpha minus under root alpha square omega square, that is minus 50, and we can call it V t. Voltage across these elements will be A 1 e to power minus 2 plus A 2 e to power minus 50, and applying the initial conditions. So, we get the V 0 equal to 5, that is A 1 plus A 2, and dV derivative of dV 0 upon dt, that is minus V 0 plus R I 0 upon R C. So, that is minus 260, and on differentiating it, d upon dt will become minus 2 A 1 e to power minus 2 t minus 50 A 2 minus e to power minus 50 t, and at t equal to 0, that becomes minus 260 equal to minus 2 A 1 minus 50 A 2, and the obtained value of A 1 equal to minus 0.2083 and A 2 is 5.208, and V t now will be the equation, the voltage equation will be equal to as a solution minus 0.2083 e to power minus 2 t and plus 5.208 e to power minus 52. And coming to case 2, when R equal to 5 ohm, alpha will be 1 upon 2 R C equal to 1 upon 2 into 5 into 10 to 10 into 10 power 3, that is 10, and omega 0 1 upon L C will be again 1 upon under root 10 into 10 power minus 3, that is 10. So, alpha and omega both are 10. So, this is the case that response is critical damped, S 1 hence alpha 1 S 1 equal to alpha 2 and that is 10, and V t will be A 1 plus A 2 t e to power minus alpha t, and applying the initial condition here. So, V 0 equal to 5 equal to A 1 and dV upon dt will be minus V 0 plus R I 0 upon R C, that is minus 100, and on differentiating it dV upon dt will be minus tan A plus minus tan A 2 t plus A 2 e to power minus tan t, and t equal to 0, that will become minus 100 minus A 1 plus A 2, and the obtained value of now will be V t equal to in bracket 5 minus 50 t e to power minus 10 t volts like. Now, coming to the third case when R equal to 6.25 ohm, so alpha will be 1 upon 2 R C, that is 1 upon 2 into 6.25 into 10 power minus 3, that is 8, and omega 0 is 1 upon under root L C, that is 1 upon under root 1 into 10 power minus 3, that is 10, and here alpha is less than omega 0. So, in this case the response is underdamped, and roots of the characteristic equation will be now S1 S2 will be alpha plus minus j omega d, that will be minus 8 plus minus j 6, and V t will be e to power minus 8 t in bracket A 1 cos 60 plus A 2 sin 60. Now, we can obtain A 1 A 2 as V t V 0 equal to 5 equal to A 1, and dV taking a derivative of d V upon dt will be minus V 0 plus R I 0 upon R C equal to minus 80, and on differentiation the equation will be d upon dt equal to minus 8 A 1 cos 60 minus 8 A 2 sin 60 minus 6 A 1 sin 60 plus 6 A 2 cos 60 to power e to power minus 8, and the obtained value here at t equal to 0 minus 80 will be minus 81 plus A 2, and A 1 is 5 and A 2 will be minus 6.667, and the final response is V t equal to 5.6 omega t minus 6.667 sin 60 into e to power minus 8 t volts like. And this is typically the response of this circuit. As you can see the voltage response, we call it this as overdamped, this we call it critical damp, and this is underdamped with respect to the time. So, that is the response of 3 degree of damping corresponding to 3 resistance in the circuit like. Now, coming to the problem 5, find the V t for t greater than 0 in the RLC circuit, where you can see here you have a resistance of 40 volt, 30 ohm resistance, 0.4 millihenry, 50 ohm resistance and 20 microfarad, and of course, typically with the switch. So, at t less than 0 the switch is open and inductor acts like a short circuit, capacitor behave like open circuit. The initial voltage across the capacitor is then the sum of same as the voltage across 50 ohm resistance, that is you can call it like a V equal to 50 upon 30 plus 50 into 40 25, and I 0 is 25 volt, and I 0 is 40 upon 30 plus 50 equal to minus 0.5 ampere, and expression for dV by dt as dV upon dt equal to minus V 0 plus R I 0 plus upon H C equal to 0. So, when switch is t equal to greater than, the switch is closed and the voltage source along with the 30 ohm resistor is separated from the rest of the circuit. That's then only becomes like you can call it the source free circuit. Once switch is closed, this is the circuit only here. So, in this case the alpha is equal to 1 upon R C, that is 1 upon 2 into 50 into 20 into 10 power minus 6, that is 500, and omega 0 is 1 upon L C, that becomes like a 354 radian per second. So, the roots now S1 S2 will be equal to minus alpha under plus minus under root alpha square minus omega square. So, that is minus 500 plus minus 354, and where the S1 is minus 854, S2 is minus 146. Since alpha is greater than omega 0, so we have a overdamped response, and we can say V t equal to A 1 e to power minus 854 t plus A 2 minus 146 t. So, we can apply the initial condition to get the A 1 A 2. So, we can say V 0 is 25 equal to A 1 plus A 2, and on differentiation we can say dV upon dt equal to minus 854 A 1 e to power minus 854 t plus in bracket minus 146 A 2 e to power 146 t. And now, applying these condition of initials dV upon dt equal to 0. So, it becomes minus 854 A 1 minus 146 A 2. So, here A 1 becomes minus 5.156 and A 2 is now 30.16, and the complete solution or response of this circuit is now of parallel circuit RLC circuit is V t equal to minus 5.156 e to power minus 854 t plus 30.16 e to power minus 146 t. Now, these are the sum of the practice problems which you can solve on the line of this what we already discussed it under different conditions. So, you can try that, and now we can say all these problems of both the side of the circuit are here, and these are the of course, some quiz questions related to that refer to the source free RLC circuit here. What kind of response will it will produce? Overdamped value are given 1 1 and C, you can find out typically I will find this, and from that it is considered underdamped. Similarly, RLC circuit R 0, then what kind of response it will give undamped response, and similarly in case of this circuit you can find out capacitance needed for that typically. So, these are the references for this, and thank you.